Hello everyone. So my name is Mansoor, and in this video we will review different topics that will serve as a basis for performing dynamic analysis that we see more often in macroeconomics. So far what we covered was primarily related to what we call the static analysis. For example, we studied the concept of optimization such as utility profit maximization by considering the case of a point in time. Similarly, when we looked at the comparative static, we sort of assumed the system moved from one state of equilibrium to another. In case of dynamic analysis, we will cover this transition from one state of equilibrium to another. How? By modeling the time path of different variables and see how they reach to their equilibrium values in the long run. So there are sort of two key words. One is their equilibrium values in the long run, another is their time path. So let's start with reviewing some basic concepts that we will need. First is about the time itself. Time can be considered as a discrete or continuous variable. Discrete variable, as we know, it will undergo change after every certain period of time, and continuous variable if it is being changed at every instant. Examples of discrete could be the federal fund rate. If we assume, as we know, that it changes after every 6 weeks, it can change after every 6 weeks, and the continuous variable example could be price of US dollar as it is being traded across the globe 24 hours. So our goals, as we know, are to find the long run equilibrium values of those variables and their transition towards those equilibrium, and then we want to find out the time path of that. The tools we have is, when we have a discrete variable, we will use difference equations to achieve those goals. And when we have a continuous variable, we will use integral calculus and differential equations. So let's start with the case of a continuous time variable. When we have a continuous time case. In dynamic analysis, what we try to find is a time path of a variable on a basis of a known pattern of change. Say a given rate of change as a derivative function. If we assume we are given an investment function which changes by this rate, which is di over dt is equals to 4t cube. And again, what we need to find out, our objectives is the time path, and then we need to find out the equilibrium value in the long run. So notice that in this case, what we have, what we call is a derived function, and where we need to reach is the investment function itself. So we need some tool which would be the exact opposite of the differentiation, which we call integral calculus or integration. For the moment, let's assume that we use those tools and we find out the primitive function of investment. It is I of t is equals to t raised power 4. From our knowledge of derivative, we know this would be true because if we differentiate this, we will reach over here. Except there is one catch, that there might be a constant in additive form attached to this original function that might get dropped out because of the derivative. For example, all these functions would give us the same derivative, 4t cubed, but they would all look different if we plot them. So we will have to attach a constant whenever we would be doing the integration. And we call that a constant of integration. And the value of this constant we will find out through using the initial conditions of investment. Those initial conditions should be given to the model or given to us. For example, we are given that investment at time t is equals to 0 has a value of 20. So we will use that initial condition and we'll try to find out the value of this constant. Okay, so let's try to find the value of the constant using the initial condition. we have this investment function, and we know the initial condition is 20. When time is equals to 0, investment has a value of 20. So all we need to do is to substitute t is equals to 0 in this investment function, and then use those initial condition, which is I of 0 is equals to 20 over here, so we get the value of c. When we substitute that value back into the original function, we get investment function t raised to power 4 plus 20. So we can see that what we have now is a complete time path of a variable of investment. Investment is being written as a function of time and a constant. Everything is known over here. All we need to do is to substitute a value of t, and then we will find out the value of investment for that point in time. The case we studied was simple, as it contained a variable, one variable and a straightforward function, but it served the purpose of explaining that oftentimes we are given the differential functions, and from there we need to trace the original functions to be able to get the complete time path of that variable. For simpler cases, we can use this integral calculus or integration, and for complicated cases, we employ differential equations or difference equation. So let's start with the first tool of integration. So as we just said, that the integration is the exact opposite or the reverse of differentiation. And if the original function was f of x, then if the original function is this f of x, and the derivative derived function is small f of x, we can integrate this function to f of x, given of course the information on initial condition. So the idea behind integration is that you can go back from the derivative function to the original function. So there are some rules of the integration that we will quickly go over. We'll review them with some examples. First is about the power rule. Again, you will find some parallels with the rules of differentiations over here. So what the power rule says is that the given function is in this form, such as it has a power x raised to power n. So all we have to do is to add 1 to the power of the variable that we are integrating and then divide it by the same. Let's review it. Of course, the n does not have to be equals to -1 in this case. And we'll see what happens when n is equals to -1. There is a different rule for that case. An example would be, we'll see if we have x raised to power 4. So we are integrating this with respect to x, and what we get is x raised to power 5 divided by 5, as we said earlier. The derivative of constant is 0, but the integral of constant would be that it will get multiplied with the variable that we are integrating with respect to. Again, we will see some parallel with the rules of the differentiation over here. The next rule that we are going to review is that, again, it's a kind of application or some variant of this power rule. So whenever we have a function in this additive form, we can do the integration by applying the integral on all of those additive terms. So we applied integral x on x raised to power 3, on x raised to power 4, on x, and then we use power rule on all of them, and then we got this result. Another example where we have a function like this. So what we can do is that we can convert this multiplicative form into an additive form by multiplying x with x squared plus 2, and then we will use the same rule as we studied over here. Because it's in additive form, we can apply the integral inside on all terms, and then we will use the power rule. And we have one more version of the power rule, and we will use that version or a variant of power rule when we have a function of this form. As you can see, we can't use power rule here, and neither we can make this in additive form. So here is a new rule for situation like this. And this rule says if the derivative of the function without powers, like derivative of, for example, ax plus b without the power n, if the derivative of this function ax plus b without the power, which is n, shows up as a multiplicative form over here, then all we have to do is to apply the power rule as it is. Since in this case the derivative of this function ax plus b was a, which wasn't there, but to bring it over here we can multiply it by a and divide it by a. In that case we can apply the power rule on that. That will sort of fulfill that requirement, and then we can proceed with the power rule. So we applied the power rule on this function, and we got ax plus b raised to the power n plus 1 divided by n plus 1. Of course, we will add the constant of integration over here. Next, we have the exponential and logarithmic rules. The integral of an exponent function is exponent function plus a constant, given x is greater than 0. And the integral of 1 over x would be log of x. One more rule, which is that if we have a function in exponent form, and if the derivative of f of x appears in the multiplicative form, as over here. So we had a function in exponent form, but the derivative of f of x appeared as a multiplicative form over here. Then the integral of whole this would be only e raised to the power f of x. We can use an example for this case. So we are given the function e raised to power 2x. As we know, the integral of the derivative of 2x is 2, and which is over here in the multiplicative form. So we can integrate this function using this rule, and we will get e raised to power 2x plus c as a result. Another important rule to remember is when we have this form where f of x appears in the denominator and its derivative appears as a numerator. In this case, the integral will be log of f of x, the function in the denominator, plus of course the constant of integration. So let's use an example for this rule. Suppose we are given a function like this, 4x divided by x squared plus 1, and we're integrating with respect to x. To apply this rule, as we know, the derivative of x squared plus 1 would be 2x. And we know 4x can be written as 2 times 2x. By writing 4x this way would let us apply this rule over here. So we can proceed and apply this rule over here, and our result would be 2 times log of f of x, which is x squared plus 1, plus of course the constant of integration. The next rule that we need is integration by parts. It's better to show it with an example. Let's suppose we have a function such that we have x times x plus 1 under root. Clearly, we cannot multiply the two terms, and thus we cannot use the rules we reviewed so far. Let's define a function x as u. This is how we proceed with the integration by parts, and that we define one function as u, another as v. So one function x, other is v, which is x plus 1 under root. And the rule we have is that integral of these two functions, u and v, which is over here, would be equals to u integral of v dx minus integral of u prime, and then multiplied by the integral of v. Then again we'll have to do a integral with u prime. So the term we need would be u prime and integral of v dx. So let's get those terms first, and then we will substitute into this formula. We know u is x and u prime would be 1. Now we move on to the integral of v. So integral of v dx would be, we'll apply that variant of power rule, because without the power, the derivative of this function, which would be 1, which is in the multiplicative form over here. So all we have to do is to proceed with that rule and add 1 to this power and then divide it by the same. So we will get the integral of v dx as this, plus integration of constants. Now we can substitute these two values over here in this expression. So let's proceed and substitute. Write down u over here, integral of v dx that we found over here, that come over here, minus integral of u prime is 1. Over here we have to just write down the integral of v dx that we found already, so we're going to just plug in over here. Now in the next step, all we have to do is to find the integral of this term, which would be again the same process that we applied over here, that without the powers, the derivative of x plus 1 is in the multiplicative form. So we will proceed and then add 1 with the power and then divide it by the same. So get the result over here. Since we are doing the integral second time, we will have another constant of integration, which we will call C2. So we can just add them together and call it a new constant of integration, such as C3. So we proceeded with the integration by parts by assuming one function as u, another as v, and we applied this formula. So there are situations like that where you cannot use the rule that we studied before. In that situations, we will apply with the integration by parts.